Hey guys, welcome back. Sorry about that. I had to go to a Google Meet, but that's okay. This is good enough for the next part of the notes. All right, so to add these together, we do it arithmetically. So that means that we just add the numbers together. So this looks like it has a max of 2. And this has a max of 2. And so when they go together, they're going to add up to 4. The width of this looks like it's 1, 2, 3, 4. So I'm going to draw them together. It's going to start here and go 1, 2, 3, 4. And then 1 over, it's going to be 4 because 2 plus 2 is 4. So I'm going to go over 1, 1, 2, 3, 4. Go over 1 this way, 1, 2, 3, 4. And then I'm just going to add it together like that. So that would be arithmetically added. Down here, these should just perfectly cancel out when they meet each other, right? Because one is a positive pulse and one is a negative pulse. So this would be positive 2, and this would have an amplitude of negative 2. So they would just cancel out to each other. It is observed that a pulse requires 0.1 seconds to travel from one end of a stretched string to the other. The tension of the string is provided by passing the string over a pulley to a weight with a mass 40 times the mass of the string. What is the length of the string? Okay, so our period is 0.1 seconds. Our velocity is related so this is tension. This is mass over length. We're saying that the tension is generated by a mass that's 40 times as much. So that's going to give me 40 mg over m over L is equal to the velocity. So the m's would cancel. And so I have radical 40 GL is equal to velocity. Velocity is also distance over time if it's a constant velocity. In this case, this would be a length over the period. So I can say that length over period is equal to radical 40 G over L. All right, we're getting somewhere. Let's square both sides. And I can cancel out an L. And multiply both sides by t squared, and I get 40 g t squared, and that is 0.1 seconds. So the length is 4 meters. So our velocity is going to be 4 meters over 0.1 seconds, or 40 meters per second. And our fundamental frequency is the one that is twice the length, right? So we're going to have 40 meters per second over 2 times 4 meters, which is going to be 5 hertz. That was a lot of work. All right, so, and I'll demonstrate this for you guys as well. This relative shift in frequency is known as the Doppler effect. This is something that you notice. So we have a person who is standing in front and a person who's standing behind, and we have a fire engine whose alarm is going off, its siren's going off. And if this is not moving, the sound waves reach these people at the same, so they would hear the same frequency. If the fire truck is moving away from this person and towards this person's going to hear these more often, and this person's going to hear them less often. So that's going to shift the frequency. It's going to have a higher frequency as it approaches you and a lower frequency as it goes past you. And again, I'll do demonstrations of this in class. So if it's a short wavelength, that means it's going to be a high frequency. If it's a long wavelength, that's going to be a low frequency. Frequency is related to pitch in terms of how we hear things. So why is this important? It allows us to determine when storms are coming towards us or moving away from us, what their relative speed is. It's used in police radar. It also has been used for us to determine that the universe is expanding and also that the universe is accelerating, because this Doppler shift is seen in the spectral analysis of galaxies far away from us. So we can tell whether something's moving towards us or away from us because we know what the spectral analysis should be. And you can see whether it's shifted to the red or to the blue. Originally, Hubble, and he gets credit for this, and the more it's coming out, he shouldn't get credit anymore, that he stole other people's work, but so is science. He studied a bunch of galaxies, and he was trying to see whether these galaxies were moving towards us or away from us, or whether everything was static. And he thought that he would find out that some are moving towards, some are moving away. And what he found out instead was that the majority, the vast majority of galaxies were all moving away from us. The irony in that is that the closest galaxy to us, Andromeda, is actually moving towards us and is going to collide with our galaxy. Later, in the 90s and early 2000s, once we had Hubble, we could see a lot more galaxies. Getting away from our atmosphere allowed us to see a lot more. And they restudied this and looked at, okay, so everything is moving away. How about we compare the galaxies that are close to us to the ones that are far away? And it turns out that the ones that are far away are moving away faster. And comparing this data to Hubble's original data, we found out that not only are these things expanding, but they're also accelerating apart. And so that requires us to have some force, right? Because F net equals ma. There must be something that is accelerating them apart. And we're still searching for what that is. So if we can figure out how much this is shifted, we can figure out what the shift in frequency is. All right, so we have two things. We have our new frequency, which they're calling f prime, and that's going to be the original frequency, and that's either going to be over 1 minus the velocity of the source over the velocity of sound, or 1 plus the velocity of the source over the velocity of sound. And this is not on your equation sheet. So you need to reason through this just by thinking about it. So if you want your frequency to increase, so if I want an increase in F, I want to divide it by a number that is less than 1. If I want a decrease in F, I want to divide it by a number that's greater than 1. Does that make sense? So if you want something to get bigger, you divide it by something less than 1. If you want it to get smaller, you divide it by something more than 1. So let's reason through a couple of these problems. The speed of sound in air is 343 meters per second. What frequency would a bystander hear from a 10,000 hertz siren that was moving towards her at 30 meters per second? Okay, so if it is moving towards you, I want an increase in frequency. It would seem higher pitched. So if I want an increase in frequency, I want to divide by something that is less than 1. And so I'm going to pick the one that is 1 minus something, right? And so our new frequency, which they're calling f prime, is our original frequency. And if I want this to be less than 1, I'm going to take 1 minus. And then this fraction is the velocity of the source divided by the velocity of sound. Or it could be the velocity you're moving towards or away from something too as well. Okay, so we're saying that this is 10,000. I want it to get bigger. It's moving towards at 30. And so this 10,000 hertz sound is going to sound like almost 11,000. So I have 10,958. All right, how about if it's moving away? If it's moving away, I want a lower pitch. I want a decrease in frequency. That means I'm going to divide by something that's greater than 1. So the bottom of my fraction is going to be 1 plus. And so f prime is going to be f. We have V source over V sound. And so now when I put in my 10,000, I get 9,195. 0.71, so I'll round that up to 96. And you can use the same thing, the same formula. Just put, if the source isn't moving, if you're moving towards the source, just make it like that the source is moving and you're not moving, right? It's all relative, right? Who's moving and who isn't moving. All right, and I'll go over this in class too when we're talking about shock waves, but sound waves. But something happens if you generate sound at the same speed that it travels. We have this buildup of pressure. And it builds itself up into this cone shape. There's actually two shock waves, but they happen so close together that you can't tell the difference. And again, I'll show you guys a video of that. All right, so some sound waves are used for imaging. They can also tell us how far underwater stuff is, like a fish finder. So if you shoot sound waves down and then they come back, you know the speed of sound in water, you know how far it is, and that's useful for us. This will help us to see what's inside, or to know what's inside of the Earth, as long as what's inside the Earth, longitudinal waves can travel through. And you hear about ultrasounds. So that's whether it's for a baby or for a tumor. If you're measuring what the thing is, you know how far these things go. I think this is a baby and not a tumor. All right, so summary. Longitudinal waves require medium. Sound is a longitudinal wave. So when I speak, I am compressing molecules, and molecules are spreading out, and it's going from molecule to molecule as it goes out to you. The pitch of the sound is relative to the frequency. A higher pitch would be a higher frequency. The loudness of a sound is dependent on the intensity. The intensity is proportional to 1 over r squared, so how far you are away, and the amplitude squared. And that's where there's a lot of worry about people that wear those AirPods, because you can imagine those distances are so small. Having those pods just a little bit closer is going to make it so much louder because of this inverse square relationship. Stringed instruments and tubes that are open at both ends are going to have the same setup for their harmonics. There's going to be a fundamental frequency where it's going to be twice the length is a wavelength, then the wavelength is a length, and then 2/3 of length is a wavelength. It'll go on and on like this. Once you have the fundamental frequency, you just have to multiply it by whatever harmonic you want. The tube is open is the same as a string. If it is closed, we have 1/4 of a wavelength is in the length, then 3/4 of the wavelength is in the length, then 5/4 of a wavelength is in the length, and it keeps on going like this. So if it's open at one end, you have a first harmonic, a third harmonic, a fifth harmonic. So it only has odd harmonics. Sound waves can interfere with each other, so you should be comfortable drawing pulses on top, also knowing what constructive and destructive interference looks like. Standing waves are a result of constructive interference. If they're off by a little, they will produce those wah, 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 wah beats. And you find out how many beats you have just by subtracting the two frequencies. So if I have a 128 and a 125, they have a 3 hertz difference. So that means you're going to hear 3 beats per second. And I picked this one because I actually have those two tuning forks. The Doppler effect is a relative shift in frequency due to one or the other object moving or both of the objects moving. And if you want a higher frequency, you need to divide by less than 1. So if something's moving towards you or you're moving towards something, if you want a lesser frequency, the objects are relatively moving apart, you're going to divide by more than 1. So it's either the original frequency, 1 plus or minus the speed of sound. The top of the fraction is the speed of the source.